Download this code from codegive.com, link in the description below. OK, let's dive into a comprehensive guide on tuning ardupilot's arducopter, multicopter, PID controllers. This is part 3, focusing specifically on the PID loops. Part 1 and 2 should cover preliminary setup, vibration analysis, and basic parameter configuration. This guide assumes you're already familiar with the concepts of PID control. Disclaimer: tuning a multirotor is an iterative and potentially risky process. Always exercise extreme caution, start with conservative settings, and be prepared for unexpected behavior. Have a kill switch readily accessible and practice in a safe, open area. Double-check your wiring, motor direction, and propeller orientation before attempting any flight. Table of contents. 1. Understanding PID control. What are P, I, and D? How they affect flight characteristics. The interconnectedness of the loops. 2. Arducopter's PID structure. Rate versus angle loops. Roll, pitch, yaw loops. The ATC parameters. 3. Pre-tuning checklist, recap and emphasis. Vibration isolation, critical. Motor calibration. ESC calibration. Battery voltage compensation. Center of gravity. 4. Tuning process, rate PID loops. Initial values. Tuning roll/pitch rate PID, iterative approach. Increasing P. Adjusting I. Tweaking D. Tuning your rate PID. Special considerations for yaw. 5. Tuning process, angle PID loops. Connecting rate and angle loops. Adjusting angle P, the primary controller. Using auto-tune, use with caution. 6. Common issues and troubleshooting. Oscillations. Wallowing. Motor saturation. Drifting. 7. Advanced tuning considerations. Filter settings. Notch filters. Dynamic harmonic notch filter. Using logs for fine-tuning. 8. Code examples, Lua scripting for tuning. Basic script for modifying PIDs. Advanced script for log analysis and visualization. 9. Conclusion. 1. Understanding PID control. What are P, I, and D? P, proportional the immediate response. It generates an output proportional to the error, the difference between the desired value and the actual value. Higher P means a stronger reaction to errors. Too high and it will oscillate. I, integral the cumulative response. It accumulates the error over time and adds a correction to eliminate any steady-state error, a consistent error that the P term alone can't fix. It's like a memory of past errors. Too high and you will get wind up. D, derivative the predictive response. It anticipates future error by looking at the rate of change of the current error. It acts as a damper, slowing down the response to prevent overshoot and oscillations. Too high can cause noise issues. How they affect flight characteristics. High P aggressive, responsive, but prone to oscillations. Low P sluggish, unresponsive, slow to correct. High I eliminates steady-state errors, example drifting in one direction. Can cause wind-up if the system is frequently saturated. Low I may not fully correct for errors. High D dampens oscillations, smooths out the response, but can be sensitive to noise. Low D may lead to overshoot and oscillations. The interconnectedness of the loops the P, I, and D terms work together in a feedback loop. Changing one parameter affects the others. Tuning is an iterative process of finding the right balance. 2. Arducopter's PID structure. Rate versus angle loops angle loop, outer loop. This loop controls the desired angle of the multirotor. The pilot stick inputs directly control the desired angle. The angle loop's output becomes the desired rate for the rate loop. Rate loop, inner loop. This loop controls the rate of rotation, degrees per second, around each axis, roll, pitch, yaw. It's a faster, more responsive loop that tries to achieve the rate demanded by the angle loop. The rate loop's output is sent to the motors. Roll, pitch, yaw loops. Each axis, roll, pitch, yaw, has its own independent PID loops for both rate and angle control. The ATC parameters. The key parameters you'll be adjusting all start with ATC, which stands for attitude control. These parameters are carefully organized by axis and loop type. Here are the important groups. ATC _ang _RLL _P, ATC _ang _pit P, angle P for roll and pitch. Outer loop gains. ATC _rat RLL _P, ATC _rat RLL I, ATC _rat RLL D, rate PID for roll. Inner loop gains. ATC _rat pit P, ATC _rat pit I, ATC _rat pit D, rate PID for pitch. Inner loop gains. ATC _rat yaw P, ATC _rat yaw I, ATC _rat yaw D, rate PID for yaw. Inner loop gains. There are other parameters, but these are the primary ones you'll be adjusting. 3. Pre-tuning checklist, recap and emphasis. This is where many issues arise. Don't skip these steps. Vibration isolation. Critical vibrations are the enemy of good PID control. Ensure your flight controller is properly isolated from the frame using soft mounts. Check your logs for excessive vibrations, CLI-test vibration. Aim for values below 30 for each axis, ideally much lower. Hard mounting or improper vibration damping will make tuning almost impossible. Motor calibration. Calibrate all motors so that their speed is synchronized at different throttle positions. Use your ESC's calibration procedure, check the ESC manual. ESC calibration. Ensure your ESCs are properly calibrated to your throttle range. This ensures that the full range of throttle signals from the flight controller is used. Some ESCs require a specific calibration procedure. Battery voltage compensation. Enable battery voltage compensation to ensure consistent motor performance as the battery voltage drops. Configure the bat_volt_ pin, bat_volt_ multiple, bat_amp_ pin, and bat_amp_ perv load parameters accurately. Center of gravity. Ensure the center of gravity is as close to the center of the frame as possible. An off-center CG will cause the multirotor to drift and make tuning more difficult. Move the battery and other components to adjust. 4. Tuning process, rate PID loops. Initial values. Start with the default values provided by ardupilot. These values are generally a good starting point. For a typical quadcopter, the default values are close to these, but check the full parameter list in your configuration. *ATC underscore RAT underscore RLL underscore P equals 0.100. *ATC underscore RAT underscore RLL underscore I equals 0.100. *ATC underscore RAT underscore RLL underscore D equals 0.005. *ATC underscore RAT underscore PID underscore P equals 0.100. *ATC underscore RAT underscore PID underscore I equals 0.100. *ATC underscore RAT underscore PID underscore D equals 0.005. *ATC underscore RAT underscore YA underscore P equals 0.200. *ATC underscore RAT underscore YA underscore I equals 0.020, YA I is often much lower than roll/pitch. *ATC underscore RAT underscore YA underscore D equals 0.000, YA D is often 0 or very small. Tuning roll/pitch rate PID, iterative approach. These two axes are tuned together, as they are very similar. One focus on rate P first. Increase ATC underscore RAT underscore RLL underscore P and ATC underscore RAT underscore PID underscore P in small increments, example 0.02 at a time. After each change, perform a small, example 20° and quick roll and pitch maneuver. Observe how the multirotor responds. The goal is to find the highest P value before you start to see fast, high-frequency oscillations. If you see oscillations, reduce P slightly. A good sign is a crisp, responsive feel to your stick inputs. If there is a slow wagging, reduce the P gain. 2. Adjusting rate I*. If the multirotor is not holding its angle well after a roll or pitch maneuver, i.e., it slowly drifts back to level or continues to drift past the set point, you need to increase ATC underscore RAT underscore RLL underscore I and ATC underscore RAT underscore PID underscore I. Increase I in very small increments, example 0.01 at a time. Too much I can cause wind up, where the integrator saturates and causes oscillations, especially in windy conditions. Test by making a roll or pitch maneuver and holding the stick. The multirotor should stop cleanly at the desired angle and hold it steadily. If you see a slow, wallowing oscillation, reduce I. 3. Tweaking rate D*. Rate D helps to dampen oscillations and smooth out the response. If the multirotor feels twitchy or sensitive, increase ATC underscore RAT underscore RLL underscore D and ATC underscore RAT underscore PID underscore D in small increments, example 0.001 at a time. Too much D can make the multirotor feel sluggish or unresponsive and can also amplify noise, leading to oscillations. If you suspect this, reduce D. A good sign is a smooth, controlled response to your stick inputs. Important after each adjustment, land and disarm the motors before making another change. This is crucial for safety. Also, make only one change at a time. Tuning your rate PID*. Yaw is often tuned differently than roll and pitch. It's generally less critical to have a super fast yaw rate. Start with rate P*, increase ATC underscore RAT underscore yaw underscore P until the yaw response feels responsive enough. Adjust rate I*. Yaw I is often much lower than roll/pitch I. Increase ATC underscore RAT underscore yaw underscore I only if you notice that the multirotor is not holding its heading well or is drifting in yaw. Start with very small increments, example 0.005. Rate D*. Yaw D is often set to 0 or a very small value. Increasing yaw D can sometimes improve yaw stability, but it can also make the yaw response feel locked in and unnatural. Special considerations for yaw. Yaw is affected by motor torque and the geometry of the frame. Larger motors and different arm lengths can affect yaw performance. If you have difficulty tuning yaw, consider the following. Motor balance. Ensure that all motors are producing roughly the same amount of thrust. Yaw rate limits. The ATC_yaw_slow_max parameter limits the maximum yaw rate. Make sure this value is appropriate for your multi-rotor. 5. Tuning process, angle PID loops. Connecting rate and angle loops. The angle loop provides the setpoint for the rate loop. If the rate loop is poorly tuned, the angle loop will also perform poorly. That is why the rate loop must be tuned first. Adjusting angle P, the primary controller. ATC_ang_RLL_P and ATC_ang_PIT_P are the main gains you will adjust here. These determine how aggressively the multi-rotor tries to achieve the desired angle. Increase ATC_ang_RLL_P and ATC_ang_PIT_P in small increments, example 0.5 at a time. After each change, perform gentle roll and pitch maneuvers. Observe how the multi-rotor responds. The goal is to find the highest angle P value before you start to see overshoot, the multi-rotor goes past the desired angle, or oscillations. If you see overshoot or oscillations, reduce angle P slightly. A higher angle P will make the multi-rotor feel more locked into the angle you command. A lower angle P will make it feel more floaty. Using auto-tune. Use with caution. Ardupilot has an auto-tune feature that can automatically tune the PID gains. However, auto-tune can be risky if your multi-rotor is not set up properly. Make sure your vibrations are very low before attempting auto-tune. Enable auto-tune. Set auto-tune_axis to 1, roll, 2, pitch, 4, yaw, or a combination, example 3 for roll and pitch. Arm the motors and take off in a stable hover. Switch to auto-tune mode, usually Alt_hold or loiter. The multi-rotor will start making small, controlled movements to identify the optimal PID gains. Let auto-tune run for several minutes. When auto-tune is finished, it will beep and land automatically. Review the new PID gains. Auto-tune will have updated the ATC_* parameters. It's a good idea to write these values down before flying again. Test the new gains cautiously. You may need to manually fine-tune the gains after auto-tune. Important auto-tune caveats. Ensure adequate battery voltage. Auto-tune puts the drone through hard maneuvers, so a weak battery will yield poor results. Be ready to take over. The auto-tune can fail, and you will want to be ready to put the drone into a stabilized flight mode. Check weather. If it is windy, or if there are sudden gusts of wind, do not use auto-tune. Monitor battery voltage. As stated above, auto-tune can be hard on the battery, so pay attention to the voltage to avoid a crash. 6. Common issues and troubleshooting. Oscillations. Fast, high-frequency oscillations usually caused by too much rate P or D. Reduce these gains. Also could be vibrations. Slow, wallowing oscillations usually caused by too much rate I or angle P. Reduce these gains. Wallowing. This is a slow, unstable movement that can be caused by several factors. Asterisk too much angle P asterisk reduce ATC underscore ang underscore RLL underscore P and ATC underscore ang underscore pit underscore P. Asterisk too much rate I asterisk reduce ATC underscore rat underscore RLL underscore I and ATC underscore rat underscore pit underscore I. Asterisk incorrect center of gravity asterisk adjust the CG. Asterisk motor saturation asterisk this occurs when one or more motors are constantly running at their maximum or minimum speed. This can lead to instability and loss of control. Asterisk check battery voltage asterisk low battery voltage can cause motor saturation. Asterisk check motor balance asterisk ensure that all motors are producing roughly the same amount of thrust. Asterisk reduce aggressiveness asterisk reduce angle P and rate P to reduce the demand on the motors. Asterisk drifting in one direction can be caused by asterisk incorrect center of gravity asterisk adjust the CG. Asterisk too little rate I asterisk increase ATC underscore rat underscore RLL underscore I, ATC underscore rat underscore pit underscore I, or ATC underscore rat underscore yaw underscore I. Asterisk wind asterisk if you are flying in windy conditions, the multirotor may drift. 7. Advanced tuning considerations. Asterisk filter settings asterisk ardupilot has several filters that can help to reduce noise and improve stability. The default filter settings are usually a good starting point, but you may need to adjust them if you are experiencing noise issues. The key parameters are ins underscore gyro underscore filter, for gyro noise, and ins underscore XL underscore filter, for accelerometer noise. Lowering these filters will improve noise, and increase latency. Asterisk notch filters can be used to remove specific frequencies of noise from the gyro or accelerometer signals. This is useful for dealing with vibrations that occur at a specific frequency. This requires careful spectrum analysis of the logs. Asterisk dynamic harmonic notch filter asterisk this can be used to automatically filter out motor noise. Requires the ESC telemetry to be enabled. Asterisk using logs for fine-tuning asterisk analyzing flight logs is crucial for advanced tuning. You can use the Mission Planner log analysis tools or other log analysis software to examine the following. Asterisk rate tracking asterisk how well the rate loop is tracking the desired rate. Asterisk angle tracking asterisk how well the angle loop is tracking the desired angle. Asterisk motor outputs asterisk to identify motor saturation or imbalances. Asterisk vibrations asterisk to assess the level of vibrations. Asterisk gyro and accelerometer data asterisk to analyze noise and identify frequencies for notch filters. 8. Code examples, Lua scripting for tuning. Ardupilot supports Lua scripting, which allows you to automate tuning tasks and create custom flight modes. Here are some example scripts. Asterisk basic script for modifying PIDs asterisk. To use this script asterisk. 1. Save the script as a .lua file, example PID_tuner.lua. 2. Copy the file to the /apm/scripts directory on your flight controller's SD card. 3. Reboot the flight controller. 4. Configure the specified RC channels in Mission Planner to correspond to switches or knobs on your transmitter. 5. The script will now allow you to adjust the PID gains in flight using your transmitter. This code associates certain RC channels to increase or decrease values for the PID loops. Asterisk advanced script for log analysis and visualization. Concept: this is a much more complex script that would involve 1. Reading data from flight logs, requires parsing the log file format. 2. Performing calculations to analyze rate tracking, overshoot, and oscillations. 3. Displaying this information on the OSD or a connected device. This requires OSD or telemetry output configuration. 4. Potentially automatically adjusting PID gains based on the log analysis, very advanced and requires careful design. 9. Conclusion. Tuning ardupilot PID controllers is a challenging but rewarding process. By understanding the principles of PID control, the structure of arducopter's PID loops, and the importance of pre-tuning setup, you can achieve excellent flight performance. Remember to proceed slowly, make small changes, and always prioritize safety. Analyze your logs carefully, and don't be afraid to experiment. If you have trouble, consult the ardupilot documentation and community forums for help. Happy flying! Okay, let's dive deep into ardupilot/arducopter PID tuning, focusing on the rate and angle PIDs and providing code snippets for analysis and experimentation, though direct ardupilot code modification is generally discouraged for safety reasons during runtime. This will be a comprehensive guide, assuming you've covered the basics like frame setup, sensor calibration, and motor direction checks, covered in parts 1 and 2 of an imaginary series. Important safety note: tuning a multirotor is a delicate process. Always remove propellers during initial ground testing. When testing in the air, start with small movements, in an open area away from people and obstacles. Have a kill switch ready. Monitor the multirotor's behavior carefully. If anything seems wrong, oscillations, erratic movement, land immediately. Part 3, Arducopter PID tuning, focusing on rate and angle PIDs. This part will focus on the inner rate PID loops, roll, pitch, yaw, and the outer angle PID loops, which are the heart of stabilization in Arducopter. Understanding the PID control hierarchy. Arducopter uses a cascaded PID control structure. This means that one PID loop's output becomes the setpoint for the next loop in the chain. For angle control, it looks something like this. One pilot input *. The pilot stick inputs are scaled and interpreted as desired angle commands, roll, pitch, yaw angles. 2 angle PID loop, stabilize PID. This outer loop compares the desired angle, from the pilot, with the actual angle measured by the IMU, inertial measurement unit. Its output is a desired angular rate, how fast the multirotor should be rotating, in degrees per second. This becomes the setpoint for the rate PID loop. Parameters like ATC_ang_RLL_P, ATC_ang_pit_P, ATC_ang_yaw_P control this loop. 3 Rate PID loop, rate PID. This inner loop compares the desired angular rate, from the angle PID, with the actual angular rate measured by the gyroscope. Its output is a motor output command, a signal that ultimately translates to motor speed adjustments. Parameters like ATC_RAT_RLL_P, ATC_RAT_RLL_I, ATC_RAT_RLL_D, ATC_RAT_PIT_P, ATC_RAT_PIT_I, ATC_RAT_PIT_D, ATC_RAT_yaw_P, ATC_RAT_yaw_I, ATC_RAT_yaw_D control these loops. 4 Motor mixer /output *. The motor mixer takes the rate PID loop's output, roll, pitch, yaw demands, and translates it into individual motor commands. It also factors in the throttle input. Diagram *. 2. PID controller fundamentals, refresher. A PID controller aims to minimize the error between a desired value, setpoint, and the actual value, process variable. It does this using 3 terms. *P, Proportional reacts immediately to the error. A larger P gain means a stronger reaction. If the error is large, the output will be large. Too high, and the system will oscillate. Too low, and it will be sluggish. *I, integral accumulates the error over time. It eliminates steady-state error, error that remains even after the proportional term has done its best. A small I gain is usually needed. Too high, and it will cause overshoot and oscillations. *D, derivative reacts to the rate of change of the error. It dampens oscillations by predicting where the system is going and applying a counter force. It can make the system more stable but is sensitive to noise. A small d gain is usually needed. 3. Tuning the rate PID loop, roll, pitch, yaw. This is the most critical step. Properly tuned rate loops provide a stable platform for the angle loop to work. We'll focus on roll and pitch first, as they're usually similar. Yaw tuning often requires a slightly different approach. Initial parameter setup. 1. Start with default values. *ardupilot comes with default PID values that are a good starting point for many airframes. Before adjusting, make sure that you have done the compass calibration, accelerometer calibration, and ESC calibration. 2. ATC_RLL_P/ATC_RAT_PID_P*. Set these to similar values initially. A good starting point might be around 0.1 to 0.2. 3. ATC_RAT_I/ATC_RAT_PID_I*. Start very low, around 0.01 or even 0. 4. ATC_RAT_D/ATC_RAT_PID_D*. Start very low, around 0.001 to 0.003. Sometimes you can even start at 0. 5. ATC_RAT_yaw_P*. Start a bit lower than roll/pitch, around 0.05 to 0.1. Your response is often slower. 6. ATC_RAT_yaw_I*. Start very low, around 0. 7. ATC_RAT_yaw_D*. Start very low, around 0. B. Tuning procedure, roll/pitch, one axis at a time. 1. Hover test. Take off in stabilize mode and hover. Observe the multirotor's behavior. Does it feel stable? Does it oscillate, wobble? Does it respond sluggishly to your stick inputs? 2. P gain tuning *. Increase P *. Increment ATC_RAT_RLL_P, for roll, or ATC_RAT_PID_P, for pitch, in small steps, example 0.01 or 0.02, until you see oscillations. The goal is to get the highest P gain possible without causing sustained oscillations. Identify oscillations. Oscillations are rapid, back and forth movements. They can be subtle at first. Listen to the motors, they might sound buzzy or rough. Observe the physical movement of the multirotor. Back off. Once you see oscillations, reduce the P gain by 20 to 30% until the oscillations disappear. 3. D gain tuning increase D increment ATC_RAT_RLL_D or ATC_RAT_PID_D in small steps. Damping helps to smooth out the response and reduce overshoot. It can also help to eliminate very fast, high-frequency oscillations that P gain alone can't handle. Overshoot test. Make quick, small stick inputs, a quick flick of the stick and back to center. Observe if the multirotor overshoots the desired angle and then wobbles back. If it does, increase the D gain. Asterisk diminishing returns. Asterisk D gain has diminishing returns. Adding too much D gain can make the multirotor feel sluggish or twitchy. Stop increasing D when you no longer see a significant improvement in damping. 4. I gain tuning. Asterisk slow drifts. Asterisk if the multirotor slowly drifts in one direction, even with no stick input, it indicates a steady state error. This is where the I gain comes in. Asterisk increase I asterisk increment ATC underscore rat underscore RLL underscore I or ATC underscore rat underscore pit underscore I in very small steps. The I gain should be the smallest of the three gains. Asterisk watch for oscillations. Asterisk too much I gain will cause slow, lazy oscillations. If you see this, reduce the I gain. Asterisk wind resistance. Asterisk a properly tuned I gain will help the multirotor resist wind gusts and maintain its position. 5. Repeat. Asterisk iterate through P, D, and I again, fine-tuning each one to achieve the best balance of responsiveness, stability, and damping. See tuning yaw. Yaw tuning is similar, but the multirotor's yaw response is often slower and less precise. 1. P gain. Asterisk follow the same procedure as with roll/pitch, increasing ATC underscore rat underscore yaw underscore P until you see oscillations, then back off. 2. D gain. Asterisk increment ATC underscore rat underscore yaw underscore D to improve damping. Yaw often benefits from a bit more D gain than roll/pitch. 3. I gain. Asterisk use ATC underscore rat underscore yaw underscore I sparingly to correct for slow yaw drift. D rate PID loop, common issues. Asterisk oscillations. Asterisk this is the most common problem. It's usually caused by too high P gain. Reduce P first, then consider increasing D. Asterisk sluggish response. Asterisk the multirotor is slow to respond to stick inputs. Increase P gain. Asterisk twitching/jittering. Asterisk this can be caused by excessive D gain or noise in the sensors. Reduce D gain. Asterisk drift. Asterisk the multirotor slowly drifts in one direction. Increase I gain, slightly. 4. Tuning the angle PID loop. Stabilize PID. The angle PID loop is responsible for converting the pilot's stick inputs into desired angles. A initial parameter setup. Asterisk ATC underscore ang underscore RLL underscore P slash ATC underscore ang underscore pit underscore P asterisk. These control how aggressively the multirotor tries to achieve the desired roll and pitch angles. Start with default values, usually around 4.5. Asterisk ATC underscore ang underscore yaw underscore P asterisk controls the yaw angle response. Start with the default value, around 4.5. B tuning procedure. 1. Aggressiveness test asterisk make quick, moderate stick inputs, roll, pitch, yaw, in stabilize mode. 2. Response asterisk. Asterisk slow/sluggish asterisk if the multirotor is slow to respond to stick inputs, increase ATC underscore ang underscore RLL underscore P, ATC underscore ang underscore pit underscore P, and slash or ATC underscore ang underscore yaw underscore P. Asterisk 2. Aggressive/jerky asterisk if the multirotor feels too twitchy or jerky, reduce ATC underscore ang underscore RLL underscore P, ATC underscore ang underscore pit underscore P, and slash or ATC underscore ang underscore yaw underscore P. 3. Overshoot asterisk if the multirotor overshoots the desired angle and then wobbles, the rate PIDs may be off. Return to tune rate PID. V code snippets, for analysis, not direct modification. Important asterisk modifying ardupilot code directly while the system is running is extremely dangerous and can lead to crashes. The following snippets are for understanding the logic, not for making live changes. Use the parameter tuning interface in your ground station. If you want to modify the code, you have to compile the software and flash it to the flight controller. A. Simplified angle PID, conceptual. B. Simplified rate PID, conceptual. Explanation of code snippets asterisk. Asterisk. These snippets are heavily simplified for illustration. The real ardupilot code is much more complex, involving filtering, scaling, and many other factors. Asterisk. DT represents the time step, the time interval between calculations. Asterisk. The constraint function limits the output values to prevent saturation and instability. Asterisk. The derivative term often uses a low-pass filter to reduce noise. Asterisk. The integral term is often limited to prevent integral wind-up, where the integral term becomes excessively large and causes overshoot. 6. Advanced tuning considerations. Asterisk. Auto-tune. Asterisk. Ardupilot has an auto-tune feature that can automatically adjust the PID gains. It's a good starting point, but often requires manual refinement. Be very cautious when using auto-tune, as it can be aggressive. Asterisk. Notch filters. Asterisk. If you encounter high-frequency vibrations that are difficult to eliminate with D-gain alone, consider using notch filters to attenuate the vibration frequencies. Ardupilot has built-in notch filter support. Asterisk. Rate feed-forward. Asterisk. Ardupilot supports rate feed-forward, which can improve responsiveness by directly feeding the desired rate into the motor mixer. This can reduce the workload on the PID controllers. Asterisk. Dynamic notch filters. Asterisk. In the latest versions of Ardupilot, dynamic notch filters can detect and suppress vibrations that change during flight, providing even better stability. Asterisk. Log analysis. Asterisk. Use your ground station to download flight logs. Analyze the logs to see how the multirotor is performing. Look for oscillations, overshoot, and other signs of instability. Asterisk. Different flight modes. Asterisk. PID gains may need to be adjusted for different flight modes, example stabilize, alt-hold, loiter, auto. Aggressive flight modes, like acro, often require higher gains. 7. Summary and best practices. Asterisk. Safety first. Asterisk. Remove props for initial tuning. Fly in an open area. Have a kill switch ready. Asterisk. One axis at a time. Asterisk. Focus on one axis, roll, pitch, yaw, at a time. Asterisk. Small increments. Asterisk. Adjust PID gains in small increments. Asterisk. Observe carefully. Asterisk. Pay close attention to the multirotor's behavior. Asterisk. Log and analyze. Asterisk. Use flight logs to diagnose problems and fine-tune the PID gains. Asterisk. Iterate. Asterisk. PID tuning is an iterative process. Be patient and keep experimenting. Asterisk. Document. Asterisk. Keep track of your PID gain changes and the resulting effects. Asterisk. Start with defaults. Asterisk. Ardupilot's default PID gains are a good starting point. Asterisk. Rate PID first. Asterisk. Tune the rate PID loop before the angle PID loop. 8. Troubleshooting. Problem. Possible cause, S. Solution, S. Oscillations. P gain too high, D gain too low, vibrations, loose components. Reduce P gain, increase D gain, carefully, balance propellers, tighten components, consider notch filters. Sluggish response. P gain too low, D gain too high. Increase P gain, reduce D gain, carefully. Twitching / jittering. D gain too high, sensor noise, vibrations. Reduce D gain, check for sensor interference, consider notch filters. Drift. I gain too low, unbalanced motors, wind. Increase I gain, slightly, balance motors, fly in calm conditions, calibrate sensors. Uncommanded movements. Sensor calibration issues, compass interference, GPS problems. Recalibrate sensors, check for compass interference, metal objects, ensure good GPS lock. Sudden loss of control, motor failure, ESC failure, battery sag, wiring problems, software bug. Check motors and ESCs, ensure adequate battery capacity, inspect wiring, review flight logs for errors, update ardupilot firmware. Disclaimer *: This guide provides general information and advice. Every multirotor is different. The best PID gains will depend on your specific airframe, components, and flying style. Always exercise caution and prioritize safety. This tutorial hopefully gives you a solid understanding of arducopter PID tuning, focusing on the rate and angle loops. Remember that tuning is a continuous process, and you may need to make adjustments over time as your skills and equipment evolve. Good luck, and fly safely.